In our previous episode, or our previous mini lecture, we talked about thin lenses and how very thin pieces of like transparent material like glass or quartz can bend light toward a focus point. And we introduced the thin lens equation. We can also apply the thin lens equation in order to understand how mirrors form their images. And this is going to be the topic of this mini lecture. Of course, you all know that mirrors form images. We've all experienced this in our lifetime. Looking in a mirror, the mirror forms an image of the real object, us. So here we have a flat mirror. Okay. Flat mirrors create virtual images. Now for a mirror, a virtual image is an image that appears on the opposite side of the mirror. So when we're looking at ourselves in a mirror, we're actually looking at a virtual image of ourselves. That image is, you can think about it as that image being on the opposite side of the mirror. You know, you look at that flat mirror and it looks like you are standing some distance away from that surface on the other side of the wall, wherever the wall is that your mirror is. And that distance that our image appears on the other side for a flat mirror is the same distance that you are standing away from the mirror on the side that you're on. So here we have a flat mirror. Here we are, this is the distance to our object on the left, and on the right, our image appears at the same distance away from the surface of the mirror on the other side. The focal length of a flat mirror is infinite. So we can also talk about the focal length of mirrors, just like we have the focal length of lenses. Infinite focal length for a flat mirror. So again, mirrors form virtual images behind the mirror surface. If this were a lens, if our image appears on the opposite side of the lens, we call that a real image. But for mirrors, we call that a virtual image. And mirrors also can form real images in front of the mirror surface. So if that image is in front of the mirror surface, that's a real image in our case for mirrors. So basically, are we real or virtual image is swapped from the case that we have for thin lenses. We can focus light to a point with a spherical mirror, just like how light passes through a thin lens and converges or diverges away from some point. Spherical mirrors can converge or diverge light away from their surfaces when the light strikes the surface. So here we have an example of a converging concave mirror. So in a concave mirror, you've got the bowl of the mirror and the light is coming in toward that bowl, toward that cave, okay? So here we have light coming in parallel to the axis down the center of the mirror. That light strikes the mirror surface, it gets reflected toward some singular point that we call the focus of the mirror. And the distance that that focus is away from the center of the mirror here, that's the focal length. Now mirrors also have something that we call the radius of curvature. The focal length is always half the radius of curvature. So if this is the focal length of my mirror, the radius of curvature would be over here at twice the distance away from the mirror, okay? And the focal length for a converging concave mirror like this is positive. Our parallel rays focus to a common point here, okay? And now we have on this side a diverging or a convex mirror. So in this case, it's kind of hard for me to bend my hand back, okay? The best I can do. So we've got the curved front surface and the light is coming in toward that curved front surface and it appears to diverge on that side and it's diverging away from some focal point on the back side of the mirror. So for our diverging mirrors, the focal length, we have the convention of giving that a negative focal length. The parallel rays coming in are reflected, and they seem to, these parallel rays that are reflected seem to originate from a point behind the mirror. So these rays get reflected off. If we could draw a line behind the mirror, they would appear to diverge away from this focal point on the backside of the mirror. Okay, so remember, converging mirror, positive focal length, diverging mirror, negative focal length. That's also the same for our converging and our diverging lenses. You don't have to have, actually really, you don't have to have a shiny surface in order to have a mirror. In fact, satellite dishes or yeah, big satellite dishes, they look like these parabolic dish-shaped objects. They are also focusing light toward a central point. That's usually where the receiver is of your satellite dish, is that central point where the light gets focused to. But in that case, when you have one of those like satellite dishes for TV, for TV or also for radio wave astronomy, that light is not light in the visible spectrum. That's not light we can see. That's light that has very, very, very long wavelengths of light, much longer than the red part of the visible spectrum. And we call those radio waves, those waves that can be reflected toward a central point in those great big satellite dishes. Radio astronomy is a very helpful and important part of astronomy. And those are these massive dishes that you can find sometimes out in the middle of deserts. And I briefly mentioned the same equations we use, the same thin lens equation we use for lenses, we can use to describe where images form for our spherical mirrors. So again, our equation for the thin lens equation, which we can also apply here, 1 over f, f is the focal length of our object, f is the focal length of our mirror or lens, is equal to 1 over do, the distance the object is from the mirror, plus 1 over di, the distance that the image is away from the mirror. And we can also use the same equation for magnification. The magnification of the image created is equal to minus di over do. It's also equal to hi, the height of the image, over ho, the height of the object. Now here is some important information that I've highlighted in red. And we have to keep track of the conventions that we use for thin lenses and mirrors because they're not always the same. So for both lenses and mirrors, DO, the distance to the object, is positive if that object is in front of the mirror or lens. For lenses, DI, the distance the image is from the lens, is positive if the image appears behind the lens. But for mirrors, DI is positive if the image is in front of the mirror, okay? So for example, here we have a converging concave mirror. Here's our object, a key. This mirror is going to create a real image. That image is going to appear on the same side of the mirror as the object. And in this case, DI is positive because our image appears in front of the mirror. And again, that's swapped for our convention for thin lenses. In thin lenses, if the image appears on the same side of the lens as the object, we call that a virtual image. There are two situations we can have for concave mirrors. Those are our converging mirrors. They look like this. The rays of light are coming in toward the bowl shape of the mirror. Concave mirrors will produce real images with a negative magnification if the object is located at a distance away from the mirror that's greater than the focal length. Here our object is sitting at a distance greater than the focal length away from the mirror, and so we're going to have a real image which is on the same side of the mirror as the object. If something has a negative magnification, that means that that image is inverted. It's upside down compared to our original object, okay? Now we can get a virtual image for a concave converging mirror if the object is closer to the mirror surface than the focal length. So here we have our object closer to the mirror than the focal length. And this situation creates a virtual image, an image on the opposite side of the mirror as the object. And positive magnification means that that image is the same orientation as the original object. So if the original object was upside down, the image is upside down. If the original object is upright, then the image is upright. Diverging mirrors always create virtual images, just like how diverging lenses always create virtual images. So again, our diverging mirror has like the curved surface pointing out, and the light is striking that curved surface that's bulging outward, okay? And those types of mirrors are kind of like the types of mirrors you see in the corners of sometimes convenience stores or like pharmacies in the corner, so that people, you know, in the front of the store can see when people are moving down the aisles and things like that. So here's an example of a convex mirror. These types of mirrors always create virtual images. So your image is always going to appear on the opposite side of the mirror as the object. Okay, so here's our object. Our image is going to appear on the opposite side. We also have ray tracing rules that we can use for mirrors. Just like how we had ray tracing rules we can use for lenses, we have them for mirrors too. And there's some different sets of rules for whether your mirror is converging or diverging, and they kind of follow along the same pattern as our ray tracing rules do for thin lenses. We are not going to play with mirrors at all in lab. We are going to play with thin lenses, and we are going to do ray tracing for thin lenses in lab, but we're not going to do ray tracing for mirrors in lab either. So I have the rules here. In class, if we were together, I would have us work on an activity in lecture where we would practice the ray tracing. So instead, what I'm going to do is I'm going to do the ray tracing when I solve some problems with convex and concave mirrors. So you can see those ray tracing activities in action together with the numerical calculations for the problems. We're going to do two problems where we practice the ray tracing and also calculate the magnification of an image produced by a concave mirror, and then the next one will be a convex mirror. Here we're going to practice a concave converging mirror with an object located inside the focal length. Okay, so here's our concave mirror. So it's opening kind of like a cave. Okay, that's kind of how I think about it. I've got my radius of curvature right here. So the radius of curvature is twice the focal length of our mirror, or you could say that the focal length is half of the radius of curvature of your mirror. Okay, so we are going to place an object 8 centimeters in front of a concave mirror with a focal length of 14 centimeters. What is the magnification? Okay, so our knowns and unknowns. Okay, we have DO, that's the distance that our object is away from the mirror. That's 8 centimeters. And the focal length of our mirror is 14 centimeters. So when we have a concave mirror, our focal length is positive. Okay, what is the magnification? So we're looking for magnification equals question mark. So our equation for magnification, we can write it as minus di over do. We can also relate it to the height of our image, but we're already given do, so we might as well get di, the distance that our image is away from the mirror, in order for us to figure out this magnification. Okay, so let's go ahead and, so I've drawn out my sketch here. Here's my mirror. This is the
midpoint down the center of the mirror. I've got my object at 8 centimeters in front of the concave mirror. So this focal length is 14 centimeters. My object is somewhere right inside here. So here I'm going to draw my object. And then this distance here is 8 centimeters. That's our DO. Okay, and we're looking for distance that our image is away from our mirror so we can get the magnification. We are going to do the ray tracing for this problem just to practice ray tracing before we get the numerical value for the magnification. Just helps us sort of get our bearings, get an estimate of where that image is going to be located. Now for a concave mirror like this, our image is real if the distance that the object is away from the mirror is greater than the focal length. Real for a mirror means that that image appears on the same side as the object. That's opposite of our convention for thin lenses. For a mirror, we have a virtual image for this concave mirror. We have a virtual image if the distance that the object is away from the mirror is less than the focal length. And for mirrors, virtual means that our image appears on the opposite side of the mirror as the object, which is different, again, from our thin lens convention. So let's use our ray tracing rules for spherical mirrors to get an estimate first of where this image is going to appear. So for our ray tracing rules for spherical mirrors, our first rule, a ray approaching a concave converging mirror parallel to its axis is reflected through the focal point of the mirror on the same side. Okay, so what does that mean? I'm going to draw my ray parallel to the axis here, and then that ray is going to be reflected through the focal point of the mirror on the same side. So it's going to be reflected through my focal point. Now, when we know we're going to have a virtual image, okay, like this one here. Whoops, I was a little bit off. When we know we're going to have a virtual image like this one here, I'm going to make a dotted line that projects me over onto the opposite side of my mirror, because I know my image is going to appear over here since we're going to have a virtual image. Okay, so this is 1. Our ray is parallel to the axis, and then it gets reflected through the front focal point. And I've got my extension of that ray on this side because we're going to end up with a virtual image over here. That's 1. The next rule, a ray approaching, and this is actually the third rule for concave lenses. I'm skipping to the third one. A ray approaching a concave converging mirror through its focal point is reflected parallel to its axis. So how do we do that? Okay, so we're going to have a ray that is going to leave this object, and we're going to imagine that that ray is leaving through the focal point. Okay, so here's the focal point. I'm going to draw my ray passing through the focal point here. It's going to get reflected here off of my mirror in this direction. And then I've got my dotted extension back here because we're going to have a virtual image. Oh, I need to extend this one a little bit further. Okay, there we go. So this is actually my third rule for mirrors. Did that one. Before I do the second rule, because the second rule is always the one that's harder for me to do without a protractor. Okay, and the second rule for both, it's the same for both converging and diverging mirrors. A ray striking the center of a mirror is followed by applying the law of reflection. It makes the same angle with the axis when leaving as when approaching. So that means that my ray leaving my object is going to come to the center of the mirror. And with our law of reflection, our incident angle is the same as our reflected angle. So if I took my protractor right here, I can figure out exactly where this reflected angle should be. So this angle right here should be the same as my reflected angle right here. Let's see how well I can do. A looks about right. I'm just eyeballing it here. Okay. And then here's my extension back to this side because we have a virtual image. All right. This is our second ray. So over here where these dotted lines converge, that's where my image for this problem appears. My image is going to appear over here. Okay, so it looks like my image is going to be larger. It's going to be magnified than my original object, and it's going to be upright. So let's test that with the numerical calculations. To get at the magnification, we have to find the distance that our image is away from the mirror. We've already know what the distance our object is away from the mirror. That was a given. So now we have to find this distance right here. This is di. Okay, so I will use my thin lens equation. 1 over f equals 1 over do plus 1 over di. I want to solve this equation for di, so I'm going to move do to the other side. So 1 over di equals 1 over f minus 1 over do. And that equals 1 over the focal length was 14 centimeters minus 1 over the distance our object is away from the mirror, which is 8 centimeters. Okay, so then this gives us 1 over di equals minus 5.36 times 10 to the minus 2 inverse centimeters. So remember, we've got 1 over di. We want to get di, the distance our image is away from the mirror. So we have to take the inverse of both sides. If we take the inverse of this side, we'll get di. If we take 1 over this number, then that will tell us the distance that our image is away from the object. And so if I do 1 over this number, I get minus 18.7 centimeters is the distance my image is away from my mirror. And this minus sign means for a mirror, we're on the opposite side of the mirror, so we have a virtual image. And that is exactly what we have here. Remember, this is the opposite convention for thin lenses. For thin lenses, if di, the distance our image is away from the lens, is negative, then our image is on the same side as the object. So the rules for that are flipped for mirrors. Now to get the magnification, magnification equals minus di over do equals minus negative 18.7 centimeters over do, which was 8 centimeters. The units of centimeters cancel on top and bottom, and then I find that my magnification is positive 2.33. So my image is upright, that's the positive, the same orientation as my object, and I've enlarged my object by a factor of 2 1/3, essentially. So I could actually come in here and measure the heights of these and find out if I've actually done that. So maybe let's do that, because we haven't done that really before. So this object here is about 5 centimeters. Okay, so HO is about 5 centimeters. Then we'll measure the height of our image. The height of my image is about 15 centimeters. Okay, so 15 divided by 5, that's 3. So you could also find the magnification is equal to the height of the image over the height of the object. And that's here, 15 centimeters over 5 centimeters. So that's telling me that from my ray tracing here, my magnification should be about 3. But I wasn't perfectly precise here on the board, and I had to use this ruler and kind of do things vertically, but that's still pretty close to my 2 1/3 magnification.